This is similar shapes, part 4, similar volumes. Let's consider these two cuboids. First cuboid is 3 by 4 by 2, the second one is 6 by 8 by 4. Look at the biggest size for both of them is 8 and 4. That makes an enlargement of 2. The middle size side 6 by 6 and 3. Compare those, enlargement by 2, and then the smallest sides 4 and 2. Again, an enlargement by 2, so therefore the cuboids are similar. So if we've doubled the length of the sides, what's happened to the volume? Is it double 2? Well, we do length times breadth times height. We get 24 for this one, and we get 192 for this one, so it's definitely not doubled. In fact, the bigger cuboid is 8 times bigger. Let's consider these two cuboids. Now you can see here that I've trebled the size of each side. And that means that the volumes are 24 and 648, still similar as before. If we've trebled the length of the sides, what's happened to the volume? Well, this time the volume is 27 times bigger. I know that by just doing 648 divided by 24. So when we doubled the length of sides, we get 8 times the volume. When we trebled the length of the sides, we get 27 times the volume. And if we continued and did it again for 4 times the sides, we get 64 times the volume. So what's the rule? Well, the rule is that the volume enlargement scale factor is the linear enlargement scale factor cubed. These numbers cubed. And of course it works for reduction scale factor as well. So in general, the volume scale factor is the linear scale factor cubed. So here's an example. Calculate the volume of the larger cuboid. So corresponding sides 7 and 4. That tells us that our linear enlargement scale factor big over small is 7 over 4, which is 1.75. Remember to cube this to get your volume enlargement scale factor. And that works out at 5.36 rounded. And since we've got a volume of 9, and this is 5 and a bit times bigger, then it's 9 times that 5 and a bit, so 9 times 5.36, and we get 48.2 rounded, and that's in meters cubed.